Yeah, thank you very much for the lovely introduction. And yeah, hello everyone, hope you're doing well. My name's Joe. Just got a little introduction about me, but won't be too long and move on to the more interesting stuff. So yeah, I'm originally from Northamptonshire. I came to Exeter as an undergraduate in 2015. I did a course in natural sciences, which is kind of a very varied degree. I mainly focused on physics and chemistry when I did that, which led to me to deciding to do a PhD roughly in the kind of physics and engineering kind of area, which started in 2020 and it's just finishing around about now. So that's why I'm a doctor almost in the introduction slides. Yeah, and since finishing that, I've recently started doing a postdoc here where I'm looking at optical computing and doing memory and computation in the same devices in computers. Also, I'm a gay man. I got married in 2021. So I think I wanted to start by just doing a little start at the kind of basics of what I mean by memory and data storage. So essentially what I'm talking about is storing information and data for use in a computer system. So it could be a PC, smartphone, any kind of electronic device. And this can be done either temporarily for very short-term use or kind of more long-term. You just imagine storing something in a hard drive, something like that. So memory is made up of kind of basic units called bits, and these are thought of to be kind of like a binary state where you can either have a 0 or a 1, which represents kind of like the two states. Which is why I've got a light switch there, which is kind of like a kind of very basic thing. We can either have it in 1 or 2 states, so you can maybe imagine that if the light is on, it's a 1, if it's off, it's a 0. So to build up like data storage and memory technology, you need to have some sort of device that can exist in 2 or more very distinct states, and it's very easy to determine which state it's in as well as that. So the other thing about data is that I often think is that how can a load of 1 and 0s make up something that actually means anything? So essentially when you have enough of these like little bits strung together, you can make up words and numbers. And also when you're using them in a computing system, you can like perform computations and mathematics and logic on these 1s and 0s to do all sorts of kind of exciting maths and stuff, which is basically how the computer is running. So I now just wanted to briefly talk about some of the kind of main types of devices when we talk about memory. So I kind of broke it down into 2 categories, one of which is for very kind of short-term storage. So that's the one on the left here in the red, the cache and the main memory. So when you have a computer, this is kind of like very short-term data storage that supports the actual running of the computer. So you have your central processing unit, and you store data very temporarily that aids the operation of this. The other type of memory, which is, I guess maybe you could call that data storage, is more kind of like your standard hard drives and solid-state devices. So this is for long-term storage. It's kind of, yeah, for when you want to store something long-term. So you can imagine like your flash drive or just your computer's hard drive, something like that. And yeah, so these things kind of exist in a hierarchy, which is how people like to think of them, where there's an offset between the speed at which something can operate and how much data it can store. So I think that triangle is quite boring, so I actually stole a different diagram that I found on the internet, which hopefully explains this a little bit better. So this is kind of like explaining how kind of basic architecture of how a standard computer would operate. So all of the kind of exciting computation and maths is done in the CPU, the central processing unit. And then branching out from there, you have 3 different types of data storage. So the first type is the cache memory. This exists in very close proximity to the CPU, and basically it's intended to be very fast as possible, so that you can get the fastest possible computation. And this is often at a trade-off of not actually having a very large storage capacity. So it's really only the very small amount of very vital data that you would store there. Moving on from there, you have the kind of like the main memory of the computer. People usually refer to this as RAM, the random access memory. This exists away from the central processing unit. It is also very fast, but not as fast as the cache. And the trade-off there means that you can store more information, but still access it relatively quickly. And the final stage is your kind of like regular storage, so like your hard drive, the solid-state device, or the magnetic hard drive. Is there the secondary memory? It's represented by like a kind of disk there. And this is very high capacity, but relatively slow retrieval, so it's mainly just used for storage of things that you're not currently using. So it's kind of like part of my intro to how it all works. The other thing I briefly wanted to talk about is just how this kind of stuff is arranged in a computer. So typically, like a computer system is made up of lots of little electronic devices called integrated circuits. These are generally like packages of electronic devices that all have like a certain function or purpose. So each of the things I described on the previous slide, they will probably exist in some form of integrated circuit where lots of electronic devices, usually something called transistors, are all packaged together onto a silicon chip, and inside your computer you can like build up the architecture by stacking loads of these things together, and they're very easy to kind of like swap in and swap out, and usually you can add more to your computer if you want to. People like to build their own systems quite a lot, I think. So these are the kind of things that you would be buying if you were doing that. Which brings me on to the Moore's law part of the talk. And it was a very good description, I think, of it in the introduction. So Gordon Moore was one of the co-founders of Intel, who are a very kind of important computing company. I don't really know what else to call them. So his prediction was that the number of electronic devices that is possible to fit onto a silicon chip or inside of a integrated circuit should double around about every 2 years. It was originally, he said it in the 1960s, where he predicted around about every 18 months, but he revised it to every 2 years in 1975. This was generally based on kind of like observations of the improvement of technology and how fast the market for computers was moving. It's not really like a physical law of science or anything. It's more of a kind of qualitative observation. But the industry's taken it very seriously as like a goal. They've tried to adhere to it very strictly, I think, because increasing performance is important and good. And it also means they can sell more computers. Since then, this has roughly remained true up to the present day, and this has mainly been caused by improvements in memory technology and also improvements in the technology used to make these devices, where we've been able to fabricate smaller and smaller devices and package them onto silicon chips to the point these days where we can have billions of transistors on a chip, and that leads to a much kind of larger storage capacity, because you have a much higher density of devices. So in most cases, each transistor on a chip would correspond to one of our bits that I described earlier. So the more you can package into space, the more you can store. So I mean, I kind of wanted to give a little overview of the history of this kind of shrinking technology, maybe very briefly, and then just lead that into kind of a description of what I have been doing and how it all kind of links together slightly. So I kind of wanted to start with some kind of like cool early technologies, which I thought were interesting. So this here, this actually predates the Moore's law, but this is one of the earliest forms of like memory. It was used for random access purposes as well as kind of static long-term storage, but it's a magnetic drum memory. So this was used in some of the first computers. So essentially what you have is you have a big round hollow drum, and on the inside of it is coated with a kind of ferromagnetic material. And inside of this storage device, you have a lot of magnetic heads, they're kind of like pointy needles almost. And they're aligned along the length of the cylinder. And they can change the magnetization of the magnetic material along the edge of the device. And by changing the magnetic state, you can encode zeros and ones, and you can store data that way. So this was the kind of thing that was used in some of the first computing systems. So I found this picture here of IBM 650, which has a magnetic drum memory. I think that's in a museum in Norway or something. But yeah, so I think the main computer is that bit on the right. That's the kind of control unit. I mean, I've got no idea how you'd use it. It's not exactly running Windows or anything. But yeah, so the magnetic drum is in there. I think the stuff on the left is another type of storage where they're using like punch cards to do maths and stuff, which is maybe goes a bit over my head. But yeah, so this is the kind of thing that this stuff was used in. It was the best-selling computer of all time at the time, selling 2,000 units for $150,000 each. Yeah. So this kind of drum memory was later kind of replaced by a different type of memory called magnetic core memory. This works slightly differently, and it can achieve kind of like a greater storage density. So this works by having kind of like a cross-section of wires. And at each cross-section you have a ring of magnetic material. And these magnetic materials can have a magnetic dipole induced in them by applying a current to them. And when that current exceeds a certain threshold, it enters a different magnetic state, and this can correspond to a different data. So this can correspond to our zeros and ones again. And each of these rings can be selected individually by applying currents from the side and from below. So when you want to target a specific ring, you apply half of the required current along the kind of X direction and half along the Y. And the only one that experiences the current is the one at the cross-section. So that's how you select the individual coils in this kind of device. However, as you can kind of see, it's kind of big. And when we talk about computers, we often think about things that are kind of smaller than we can see. So this was the kind of thing that was around in around the 60s, I think. But after that, we moved on to different types of data storage, the kind of stuff that is still used today. So yeah, the main thing that replaced the magnetic core memories is DRAM. So this stands for dynamic random access memory. This is the kind of thing that's still used in computers today, but it came in around the kind of 1960s, 70s was when the first commercially available ones were around. So this is the kind of memory that's used to support the operating of the system rather than the long-term storage type. So each cell, each bit of DRAM consists of one transistor, which is a type of electric component that can act as a switch, which means that you can either have a current flowing through it or you can not have a current flowing through it. And that's linked to a capacitor, which is a type of electronic component that stores electric charge. And what you do is when you want your bit to be 0, you leave it as it is. When you want it to be 1, you activate your transistor, allow the current to flow into the capacitor, and that stores the electric charge. And this corresponds to your one state because we've got a distinct difference that we can detect. But perhaps one drawback of this technology is that it is dynamic, which sounds good, it sounds exciting, but it's actually bad because these capacitors, they tend to leak the charge over time, which means that they need to be continuously refreshed, which means you need to keep on reapplying this electric charge to the capacitor. So this is the kind of technology that over time, according roughly to Moore's law, has been shrunk down to smaller and smaller sizes. So this is the first commercially available one here, Intel 1103. So this is the first DRAM integrated circuit. And that can store 1,000 bits, which isn't very much on the terms of what we can do today. But moving forward, this shrunk down to smaller and smaller until today we have something which is called the 3 nanometer technology node, which is more than anything maybe a marketing gimmick these days from semiconductor companies where they say we can make things that are 3 nanometers big. That's the smallest thing we can make. In reality, it's perhaps a little bit larger than that. And it's more of just, they want to say it's better than the last one. But it is an improvement. And, today we can have up to, I think a computer has 1632, 64 gigabytes of random access memory. These days, this technology is hitting a bit of a wall where they're finding that they've reached some fundamental limits with how much they can shrink it, which is going to be maybe a theme with Moore's law in the upcoming years. One idea is that they want to start stacking stuff on top of each other. So instead of just moving stuff into a smaller and smaller area, they want to think about, building rows and rows of it on top of each other. They call it a high bandwidth DRAM, which is a little bit of a strange name to me, but it's interesting to see whether this is something that can be fabricated and made commercially available. I don't know, but it's quite an exciting idea, I think. And I just wanted to give another overview of a slightly different type of memory as well, which is the flash memory. This is your solid state devices that all computers are kind of moving onto these days. But it's been around for a long time. It's the kind of technology, like the thumb drive that I brought my PowerPoint on today uses it. And the example of how this has been scaled down I wanted to give through, I remember when I was a kid I had a PlayStation 2 and this came with a kind of memory card that you slot into it and it can store 8 megabytes of data on it. And this was enough to store the data from all the games you wanted to play ever. Comparing that to now, which is the most recent, is the PS5, I believe. And this is a picture of someone putting a 1 terabyte flash drive into their PlayStation 5. So, I think that's maybe a more kind of interesting way of seeing how the capacities of these technologies has increased. And I just got this down at the bottom. This is a description of how the flash memory works very quickly as well. It relies on trapping electrons in a conductive gate called a floating gate. So essentially you have a device like this, which is a transistor, and you have a current flowing from the source to the drain, which is on the right there. And when you apply a voltage across the top of it, you can cause electrons to tunnel up into this top red and yellow region, and they get stuck there. And this is how you kind of distinguish between the 0 and 1 in this case. But it's a very brief. So this is moving on to kind of more into the realm of what I do. Because there's been a lot of panic in recent years about whether we're still going to be able to shrink devices down and meet this kind of expectation that we set up for ourselves at this point with Moore's law of can we get better storage every 2 years. And there's a lot of fundamental limits that are starting to be reached with the kind of devices that we have at the moment, that basically they're just getting so small that a lot of the ways they operate are kind of breaking down in various ways. So yeah, when we're getting small enough, for example, you're getting currents flowing through these devices when you don't want them to be and they're not meant to be. And all sorts of other problems like the barrier that you need to overcome to get them to operate is becoming more and more reduced. And another example is in the DRAM earlier, when that's getting smaller and smaller, it's harder to store any charge in the capacitor. So there's a lot of challenges that need to be overcome. However, the kind of scientists and engineers have also been thinking, you know, is this the only way that we can do things? Is this the only way we can store data using transistors and continuously shrinking them? Or do we need to start looking at different types of technology, which is more of the area that I have done a lot of my work in. So what has happened a lot in recent years, probably I would say the 21st century, is people have been looking at new types of data storage technology. And the example I'm going to choose to talk about is phase change materials, because that's what I did my PhD in. These are materials that have been used to make a new kind of memory that's completely different from the kind of transistor-based stuff. So phase change materials are usually made up of these three elements here, so germanium, antimony, and tellurium. They're kind of like semiconducting materials. But the key property of these materials is that they can exist in two states, which is good for our memory. The first state is the atomic order of all of these atoms of germanium, antimony, and tellurium can mean a very disordered state, which is called an amorphous state. This happens to have a very high electrical resistance, which means it's hard to create an electric current in it, to flow electricity through it. And the other state that it can exist in is a crystalline state, and this is when the atoms become very ordered. This happens to have a low electrical resistance, a lot easier to flow a current through it. And the great thing about this is it's a reversible process, switching between the two of them. You just need to apply heat in various ways, and you can switch between the two of them. And this is, I think, a picture of some GST, germanium anti-tellurium, according to Google Images, in a dish. So this can be used to make a new kind of technology, the kind of stuff that I've been making and testing in my time researching at Exeter. So I have an overview, kind of the basic device overview of how it works. Which is shown here on the right. So essentially what you do is you get your phase change material and you just sandwich it between two layers of metal, which act as electrodes that you can apply an electric current to. And by flowing a current through this material, you can cause it to heat up because the energy is transferred to the material as it resists the flow of electricity through it. And this can cause our transitions between our amorphous and our crystalline states. And by doing this, we can cause this entire device to either have a very high resistance, where it's hard to flow the current through it, or if we heat it up enough, we can cause it to crystallize and be in the crystalline state. And this is very different, and it has a lot easier time having a current flow through it. And these two states can correspond to our 0 and our 1, making up a bit of memory. So this is a different way of storing data that's not really relying on tiny, tiny, kind of intricate devices. It's relying on some bulk material properties. So due to this, this reduces the need for very small, very compact electronic components and very complicated manufacturing techniques. And it's easier to make smaller and smaller devices because you just need the material itself in there. So this has caused there to be a lot of interest in recent years in a potential different kind of memory technology to how it's been done for the last 40 or 50 years. There was even some of this material some of this technology was commercialized recently. It didn't quite work out, but there was something called Intel Optane that used phase change memory. This was kind of supporting, it was the intended use of it was to support data retrieval from the hard drive. And I think it sold fairly well, but they did end up discontinuing it in recent years, unfortunately. But hopefully there will be some more phase change memories coming soon. I'm not sure. But these are, the kind of devices that I've been making as part of my research. This is just a kind of brief overview of the switching mechanisms between the two states. But essentially you just need to apply a current and you can switch between the two states. So to go from amorphous to crystalline, you just need to apply a current that causes the material to go above a certain temperature, and then over a extended-ish period of time, a few kind of 100 nanoseconds or something, you change state to the crystalline. And then when you want to go back to the amorphous, you apply a larger current which melts the entire device, and you go back to the amorphous if you cool it quick enough. So this kind of leads on to more of the kind of thing that I've been doing, which is looking at flexible electronics. So this is essentially just kind of electronic devices and circuits that are printed on bendable surfaces. So you can see kind of in the bottom right here, we've got some sort of a flexible substrate, and they've built memory devices on top of that. Phase change materials have also been proven to be able to withstand bending and still function kind of after they've been bent many, many times in many, many cycles. This is, I think that image there is demonstrating that, the one on the right, where they've taken this kind of like a sheet of devices and they've wrapped it around a very kind of like thin cylinder. And after testing the devices, after they've undergone this strain, they've been proven still to work. So these are the kind of devices I've been making in my PhD, although it's not my images. And why do we want to do this? Well, there's been, maybe in the last 10 years or something, people have been talking about something called the Internet of Things quite a lot, which is, the idea of that is kind of extending smart capabilities to a very wide range of electronic devices, or devices that you wouldn't necessarily assume had that kind of thing. So it can be like wearable technology or anything like that. And this has kind of like a wide range of applications. There's a lot of interest in this kind of thing in healthcare, especially because you can have devices that can do medical monitoring or stuff like that attached to clothing or things around people's wrists and stuff like that. And one key component of this is going to have electronic devices that can withstand the bending, like the ones described previously. And there's also another wide range of things you can do. So there's a lot of interesting kind of using it for sustainable applications. So you can help you have reusable packaging, stuff like that, where you, for example, have plastic and glass, maybe bottles or something, which go through a cleaning and reuse cycle. And if you have a kind of electronic chip attached to these devices, you can kind of track what kind of treatment they've gone through, what they have been used for previously, whether they've been cleaned and treated before using the next one, and all this data can be encoded in a memory that is attached to the device, attached to like the bottle, I mean. So it's kind of like a wide range of things. Essentially, you can make anything you want have some kind of like increased capability by incorporating a electronic capability into it. So the company that I have been working for is interested in kind of like tracking products through the production process. So if you can embed a chip in it with something called an RFID, you can kind of track something as it goes through a manufacturing process and encode data into that, tells you what's happened to it, what it needs to go through next, that kind of thing. Yeah, so I think that's kind of all I wanted to say. So I guess in conclusion, yeah, we're looking at shrinking electronic devices, and as a part of that, we looked at new kinds of technology which can fulfill this need, but also it's introduced a lot of other ideas to us beyond just shrinking things. We can do all sorts of exciting things with everyday objects. Yeah, thank you very much.